to the class STEM Cafe where we make everything science, technology, engineering, and mathematics easy to comprehend, assimilate, fun, and entertain. We're still continuing on the topic on the subject of calculus, but today I would really like to summarize the results we have gotten so far from differentiation and introduce you to integration. Now, let's start. What is integration per se? Integration is the reverse process of differentiation. That is, we are trying to get back to the initial function, initial equation that was differentiated. What am I trying to say? We have a function like this, fx, and we differentiate it with respect to x. So, we always represent this like this. Now, what we did to get this is differentiation. Differentiation. But we are not trying to work this back to this. That is what we refer to as integration. That is, we write it like this to give us this. That is what we mean by integration. But in integration, okay, now let us now remove this. Let us call it normal function or whatever. Okay. Let me leave it like this. This one is always referred to as this. In this stage now, that is, we are integrating it. We refer to it as integrand. Then, what again? Let's look at a function like this. X squared plus 3x plus 4. Let us now differentiate this. Let's differentiate it. Equal to 2x plus 3. So, if I want to return it back, it is the reverse process now. When I wanted to differentiate this, I brought these two here, and then I subtracted one from these two to remain at the power. That is, x raised to the power n will give me, first, I will bring n out, then I will subtract one from the n. Remember, just like when you are doing something like change your subject or formula and so many other transactions like that, like change logarithm, change of base of logarithm and all this stuff. So if you want to reverse back to this, you start from the last thing with it. What will you do? The first thing is you add 1 to this power. And then you will now divide this by, because it is what you brought here, by n minus 1 plus 1. That is how you got this. So when you want to reverse it back to this, that's what we do. But note, after we have done all this, to get this 4 will be difficult. Because we don't know what it is. It might be 2, it might be. So, we don't have any definite figure for it. So, I will need to do something. Now, let's work it back. 2x plus 3. Let's now work it back. I will do it for the first one. That is x plus n. So it's going to give me x squared plus 3x. You know I've got that one. Plus k. You always put it there. That constant. Because I don't know what generated, what was removed from it. It can be 0, it can be negative number, it can be positive number. So we always put it there. And we refer to this as indefinite integral. As it is like this. But you can find the value of k. If you are given, like, when x is equal to 5, fx is equal to, fx, if x is equal to 0, fx is equal to 4. So from this, after getting to this place, we will now substitute 0 for this to get k. That is the way to do it. And some instances, we might not even need to find k. Like, if we are given the value of fx at 2x situation, at 2 points of x, like when x, like, okay, if you have asked to find the value of the difference between fx for x equals to 1 and x equals to 5, you realize that the k value will be struck out. So in some instances, you might not need to find the value of k. But most of the time, after you integrate, always put k. Now let me go to, since we know that integration is the reverse process of differentiation. Let us consider the results we have gotten so far and how we got them, so that we will find integration something fun. So, this is just introduction to integration. Introduction to integration. So you can see, and this k is constant of integration. So at every point in time, please don't forget, every point, always put k, so that you will remember either to find the value or not to find the value. And as it is, that's why you refer to it as indefinite integral. Now let's look at the results we have gotten for differentiation. Now let's quickly look through the summary of the results we have derived. When we have constant c, dy dx is 0. Please, just for interest case, if you have been following from beginning, you can copy it somewhere. If you have known it, no problem. X raised to power n, x raised to power n minus 1. X raised to power n is an, x raised to power n minus 1. That is, a is a constant. Sin x is cos x. That is, differentiation of sin x is cos x. For cos x, we have minus sin x. Tan x, sec square x. E raised to power x, e raised to power x. E raised to power k x. It should be e raised to power k, e raised to power kx. A raised to power x is a raised to power x ln x. Ln x is 1 over x. That is, differentiation of ln x is 1 over x. Log ax is 1 over x ln a. Cos x is minus cos x square x. Sec x is sec x tan x. Cosec x is minus cosec x cos x. Sin x is cos x. That is, the differentiation is cos x. For cos x is sin x. Arc sin x is 1 over root 1 minus x squared. Arc cos x is minus 1 over root of 1 minus x squared. Arc tan x is 1 over 1 plus x squared. Now, for arc sin x is 1 over root x squared plus 1. Compare it to this one. You can see. For arc cos x is 1 over root x squared minus 1. And arc tan x is 1 over 1 minus x squared. So compare it to this one. So you can see, this is just summary of the results I have derived, and I also try to explain some other things now. Try to know this, and if you don't, you might not need to memorize everything. Learn how to derive them if you don't know them. Now let's look at some other results we derived. We talk about product rule. That is, when u and v are functions of x. U and v are functions of x. Are functions of x. So this is what we do. U dv dx plus v du dx. Quotients, that is u over v. U and v are still functions of x. So this is what we do. V du dx minus u dv dx over v squared. This one is O. Now for implicit function. Implicit functions means that if you have combination of x and y together, so we don't need to start finding making y the subject of the formula before we differentiate. So we are going to have like anything like this. It might be x raised to the power n, y raised to the power n, or whatever. It might be like that. Anyhow. So, but what I want you to know is this. You are going to use product to do the differentiation of the implicit parts. Function of function. That is, if you have a function f, y is like this. F gx. You can see. So, dy dx will be dy df times df dx. Do you understand now? So, this is used in so many other, in deriving some other results. Everything we use here is used in deriving the previous results we looked at, and some other ones that will be shown. Parametric equation. In this situation, y and x, they are function of another parameter. Now, like this one, y is a function of t. X is a function of t. You know, we cannot quickly try to make x and y the function of x every time. So, for it, what do we need to do? We find the y dt and we find the x dt. So, by multiplying, just like what we did in function of function, you know, we call it share rule. That's what we do here. dy dt times dt dx. I know dt dx is reciprocal of dx dt. That is equal to 1 over dx. That is get here. Now, if you are going to do the second derivative, the 2y dx squared, we do the dx, dy dx. So it should be d dt, dy dx times dt dx. You can see. So I deliberately brought this up so that it will refresh our memory. Now let's look at some other ones. Now to conclude the summary, let's look at this. Logarithmic differentiation. This depends on the fact that d dx ln x is equal to 1 over x. That is why we differentiate ln x, we get 1 over x. And then when we differentiate ln f, that is a function of x, we are going to get 1 over f df dx. You can see this result comes from this place. Therefore, this is an expression. Why? So if we want to use this one here, what are we going to do? We will express it as ln. And after that, we will now gather all the necessary parts together. At the end of the day, we are going to have dy dx out here, and dy dx will be equal to y multiplied by everything here. Y will multiply everything here. So it makes our work is very easy. And try to see how if there can be a space for me to do that. So at the end of the day, we are going to have something like this: dy dx will be equal to y into 1 over u du dx plus 1 over v dv dx minus 1 over w dw dx. You can see it's very, very easy. Very, very easy. And if you look at this, y divided by u is going to give you v over w. So you see, it's very easy. I like using that one, especially when product and division is involved. And when I have many functions like this together. Else, you can go and use product rule or quotient rule. So, if you apply this one into this one, UVW, you are going to get this straight. You are going to get UV dW dx plus UW dV dx plus VW dU dx. Now let's look at the general application of function of function. General application of differentiation to function of function. Because sometimes you might find it might take you time to recognize that you are going to use function of function in certain situations. That is why I listed this one. In a situation, here f. Now look at this. Here is a function of x and it's raised to power n. What we just need to do is dot 1 from the power, multiply it by n, and then do differentiation of f. Same thing here. The only difference is a, which is constant. Now, look at this, sin f, cos f, df dx. You know, f is a function of x. That is why you have it like this. Same thing here. Tan and e raised to power f. That is f function of x. So after, when you do e raised to power x and you differentiate it, it's still going to give you e raised to power x. So we now differentiate and multiply e raised to power f with the derivative of the power. So with this, I think we have covered major, results of the differentials and the technique of getting the differentiation. Now let's look at integration proper. As I've said, integration is just a reversal of differentiation. So when we are looking at the differentiation now, we just need to return it back to the initial function. Like if I'm going to integrate a function that looks like this, I must get this. That's what it is. If I'm going to integrate a function that is like this, I must get this. And after we have the standard results. You now look at some other techniques involving more involved, functions or functions that are not that common or we don't have standard results for. Now let's look at what I mean. Now let's look at a very simple integration. We start from that of the polynomial. Of course, we can do that of a constant. Like if I have fx, okay, if you have to integrate this, it's going to give you 7x plus c. So that's why I'm not starting from that one. Now look at this. It involves cube, square, x, and just ordinary figure. So if we are to differentiate this, what will it give us? We are going to do the normal thing we said before. We are going to do something like this: 4x raised to power 3 plus 1 divided by 3 plus 1 plus can see that is what it is. It's a very simple way. For all of this, it's very simple. Now, for us to find C, we have been given some predetermined results. And because we can do this, it's very applicable. That's what makes integration and differentiation very applicable in almost all the fields. Almost all the fields. I don't even know, maybe they apply it in law or language. But I know when it comes to science, anywhere you see calculation, anything, it's very applicable. Now, this is this indefinite integral. Now, to find the definite figure of this, you have been given certain situations, that is, when x equals 0, y equals to 4. With that, you can find C. Therefore, you can say 4 equals to 0 plus 2 times 0 plus 0 plus 7 times 0 plus C. Therefore, C equals to 4. You can see. Very easy. Now, we have to find y when x equals to 1. So, before we go into that, we can now give the real expression for y. So, y will be equal to x raised to the power 4 plus 2x cubed plus x squared plus 7x plus 4. So we can leave it like this. Now, when x equals to 1, what is the value of y? We can easily do that now. So y will be equal to 1 plus 2 into 1 plus 1 plus 7 into 1 plus 7 into 1 plus 4. And that gives us 1 plus 2, 3 plus 1, 4 plus 7, 11 plus 4, 15. So you can see, very interesting. Very, very interesting. And from the standard results you have worked on, when we discuss standard results of or derived results of differentiation, you can easily walk back and get your results straight. Now let's look at another one. Now let's look at a function of a linear function of x. You know, if we have an expression like this, x raised to the power 4, yes. If we should integrate this, let's say I, it's going to give us x raised to the power 4 plus 1 over 4 plus 1 plus C, which is x raised to the power 5 over 5 plus C. Now, assume you have a linear function like x plus a or nx plus a raised to the power 4. Raised to the power 4. You can see that this one still has the power of 1. This one still has the power of 1. So it's very, very easy to handle. Very easy to handle. And what do we do? Just like we did in function of function differentiation, we will change this one to maybe x or u, to maybe uv or anything, and then we will do it like this. Let me show you. Let's assume we have something like this: x plus a raised to the power 4. Yes. The first thing is to make this one u. Let me make it. Let's assume I have something like this: 3x plus 2 raised to the power 4. Yes. The way to go about it is this. I first of all express this like this. Let's 3x plus 2 equal to u. You can see. So, let me now differentiate with respect to x. At the end of it, it's going to be 3 to be equal to the u dx. You can see. So, I will now make the x the function of this thing, of this equation or expression. So the x will now be equal to the u over 2. You can see. So what I have here, I will now bring it into this expression. What do? I will be equal to u, because that is my u, raised to the power 4. What is my dx? The u over 3. The u over 3. You can see. Now, I can now make it, to make it easy, I can now make it like this: 1 over 3 u raised to the power 4 du. So it's going to now be equal to 1 over 3 u raised to the power 4 plus 1 over 4 plus 1 plus k or c or anything. You can see. And that's going to give me 1 over 15 u raised to the power 5 plus k. And that's going to be, what is my u? 3x plus 2 raised to the power 5 over 15 plus k. So when you have function of a linear function, you can easily work on it like this. So it makes our job very easy. So we have done that of linear, what's it called? Polynomial expression. And now we have done that of function of a linear function. Now look at this. We have I equals cos 3x dx. So let us make 3x to equal to u, because this is the expression for 3x. Now, what will be our You can see we are working it back to what we got the expression from. Now, we can now say I cos u du over 3. You can now equate it to be 1 over 3 cos u. And you know, we got cos when we differentiated sine. So we are working it back to that. So it's going to be 1 over 3 sine u plus c. And what is our u? 3x. So which is 1 over 3 sine 3x. So you can see. Now, if I have differentiated sine 3x, sine 3x, it will give me 3 cos 3x. So, for me not to have 3 here, it means that this one has been divided by 3 before. Can you see? I'm just trying to let you see the reverse process. So, it makes this one I've done. I don't need to start stressing myself about the thinking. It has been made simpler now. So, I would have used something like function of function or anything to get it. But look at how it is now reversed. In a very simple way. A very simple way. So, this is just to introduce you to integration proper. Please, if you have not subscribed, kindly subscribe, comment, share, and follow. If you know anybody that will benefit from this, please let them know. The only way you can encourage us to be on, to be available as often as possible is to do this. That's the way you can show that you appreciate us. Thank you very much. For those who have been following, thank you very much. Comment. If you have any question, you can direct your question to us through the channel in the description.